So greetings everybody and welcome to the afternoon sessions for this hall. Right now we'll have open source robotics with Python, learn robotics with no robot required. My Kat Scott here, developer advocate for the ROS project. So we welcome Kat on stage to start her talk and we hope that you enjoy.
Hi. Let's get this adjusted. Thanks. So, like you said, I'm Catherine Scott. I work at an organization called Intrinsic, but I primarily work on the ROS project. You can find me as KScottZ on most platforms. I'm going to say I've just packed a ton of information into 30 minutes. I'm going to be flying through it. And I basically made sure to put links to every bit of documentation that I was using through here. So if something's not clear, there's a source code, there's a documentation. You can go clarify it for yourself. Oh, and on the right is the logo for our latest ROS release. But we have another ROS release, a big one, coming out on Thursday. So I work with a lot of people who are trying to develop robots or want to learn robotics, and a lot of people don't always have a mentor. They may not have a university that they're going to. And I find that probably the easiest way to learn robotics, if you don't have those things, is just to start taking robots apart and putting them back together. So I put together a talk that allows you to take robots apart and put them back together and learn about ROS. So most robots, if you haven't seen a robot before, they're divided into two parts: hardware, software. The problem with hardware, as software developers, we think hardware is, it's so much fun. It's so much fun. When you're sitting on a cold, dirty floor at 2 a.m. trying to find a 3mm Allen key, it's not as fun as you think. Sometimes hardware can be a pain, and especially it can be a pain when you're trying to debug things. So what we've done for this talk is I've replaced the hardware with also software. We're going to be using an open source project called Gazebo. And then for the software side of this talk, we're going to be using ROS, or Robot Operating System. So what are ROS and Gazebo? So ROS, which stands for Robot Operating System, is a free and open source software for programming robots. It has been around for over a decade. It's probably one of the most widely used robotics frameworks in the world, and it works with a ton of different programming languages, primarily C++ and Python, and has a rich package infrastructure or ecosystem just like Python. Gazebo is one of many robot simulators that are out there. You can think of a robot simulator as just a video game with better physics, but it's just this visual thing that you see, plus objects that are moving around and have realistic physics, and you simulate every part of your robot inside the simulator. Gazebo is kind of well known for being very modular and easy to configure to do lots of different projects. So when I say robot operating system, it's kind of a misnomer and kind of not. ROS is basically an operating ROS isn't an operating system, but it's more like a layer on top of an operating system, normally Linux, normally Ubuntu, that makes building robots a lot easier. ROS has a bunch of command line interfaces and tooling that allow you to debug and monitor and introspect and log data from your robot. Up on the far left of the screen is a TurtleBot 1. So this robot's probably 12, 15 years old. And if you look at the far right of your screen, there's a robot that's, I believe, from Zebra or Fetch Robotics. One robot inspired the others. So Fetch, if you've gotten a package delivered or gotten something that may have been built in a factory, it's very likely that a robot like the one on the right actually delivered the parts that were used to build that thing. And it was probably using ROS, and it was probably, some of that work was derived from the original TurtleBot. So this ROS is a relevant tool to building robots that are used in the real world. And the good news is, since it's PyCon, ROS plays well with Python, Gazebo plays well with Python, and so we have a good talk. So in robotics, robots generally do three things. We call this the sense, think, act paradigm. So the robot senses stuff, meaning it has sensors. These can be as simple as a switch, or as fancy as a huge $100,000 spinny Velodyne LiDAR that sits on top of a self-driving car. But all of these things just pull in information from the environment. You write a bunch of code to think about all that data that you're seeing, and then the robot acts on that data. So you make something happen in the real world. It can be as complex as doing a bunch of kinematics to move a 6-axis arm. It can be as simple as moving a servo. So that's my broad sort of definition of robotics. So what are we going to do today? So today I'm going to show you how to make a simulated robot in Gazebo, interface that simulated robot with ROS2, and then I'm going to show you how to make that robot do stuff. More specifically, we're going to figure out how to figure out where the robot is, how to make the robot move, and how to read sensor data and respond to it. And that'll be a little bit quick right at the end. So what I'm not going to do, I'm not going to fuss with installation. I've put together a Rocker container. Rocker's like Docker, but it's basically Docker with GPU support and GUI support. This is not going to be a super deep dive on all these things. This talk is meant to be a teaser to get you to go look at the actual documentation for projects like this. And all the resources are at that quick link, and I'll keep flashing that if you want to go take a look. So I'm going to start by clarifying a few things, because with robotics, there tends to be a lot of jargon. With the new robotics framework, there tends to be a lot of jargon, but it's all stuff you're familiar with. So Python, we have virtual environments. You use virtual environments to keep your working area clean. You put all your requirements in there. ROS has the same concept, it's just called a workspace. And usually it's a directory with _WS in it, but same thing. It's just a virtual environment to keep all your data. So Python has pip and pypy. ROS generally works by apt-get install for packages, and we also have our own index of packages called ROS index. So if you're looking for perhaps a ROS package that runs a particular kind of camera, it's probably on ROS index. So Python, we write programs, shell scripts, something like that. In ROS, we call them nodes, and the really short version of that is because ROS is a bunch of programs, a bunch of nodes in a directed graph, and the graph edges are data moving through the system. So we call them nodes. But whenever you hear node, just think program. And the last one's probably the most tricky one. If you've worked with, say, ZeroMQ, RabbitMQ, Celery, if you know what I mean when I say pub/sub, most of ROS is just pub/sub. So look at, and those pub/sub features are called topics. So today we're going to be working with a robot called the Turtlebot 4. This is a robot that's a collaboration between the Open Source Robotics Foundation and ClearPath Robotics. I'm not trying to sell this robot. You can buy one, you can build one because it's open source, and most importantly, you can use the simulator to play with this robot for free. There's extensive documentation and a whole manual on how to use it. I have a link for that below. Really quick, the robot is basically an iRobot Create 3, which is a vacuum robot without the vacuum, a depth camera, a 2D LiDAR, a Raspberry Pi 4, and a breakout board. It's not incredibly complex. So let's start with the container magic. I'm going to gloss over this a little bit. Ordinarily, to get ROS running, you need to install a particular flavor of Linux, install ROS, install Gazebo, install all the dependencies, install your dev environment. We've collapsed that all down into this Rocker container, and this Rocker container can work with and without a GPU. I intentionally built all of this on my 7-year-old laptop without a GPU, so I'd be reasonably certain it would run on most commodity laptops, like the commodity laptop your kid might have. So first thing we do is we set up the container. I'm not going to go through this line by line, but essentially it's install Docker, install Rocker, install the source code for the project, build it, and then open up a shell into the Docker container. Once you're in the container, you're basically running in a ROS workspace. So the first thing you have to do is tell ROS, I'm using this ROS workspace. And the way we do that is by sourcing a setup.bash file. We're then going to call a command called colcon. Colcon is ROS's build tool. And you need a build tool because ROS is interspersing C++, Python, lots of different messages. And this tool basically makes sure that all of these different moving parts, all these different programs know about the environment that they're working in. So just kind of take it as gospel for right now. It's sort of an advanced subject, but if you wrote a bunch of code and you want to see it work, hit colcon build. And then the last thing is I want to call our first ROS command, which is going to be ROS2 launch Turtlebot 4 ignition bring up, which is the package name. And then we're going to launch a file name, and I'm going to give it one parameter, maze. And if you've done all this correctly, what you will see on your screen is this video game looking thing, which is actually a full simulation of the Turtlebot 4. write down, I mean, it simulates the commands that are in there, it simulates a lot of the physics and dynamics that are in there. You can basically use it as a real robot. It's a lot easier sometimes to write code with a virtual robot than it is to be sitting on the floor trying to run commands. All that gobbledygook on the right-hand side of the screen, that's just the interface for the robot. I'll show you a little bit more about that in a second. So the first thing we're going to do, we want to write a ROS Python package. So we're going to open up a new terminal inside of our Docker container. We're going to source the setup.bash file. We're going to move to the source directory, and we're going to have ROS set up all the code to actually build our Python package. So we go ROS2 package create, and we say build type, Mint Python. That's sort of ROS's Python tool. We give it a license, because we automatically track some of the license stuff. And then we give it a name. The first name we're going to give it is the package name. So our package is going to be called TB4Toy. So remember, that's the package name. And then the ROS node, the ROS program that we're going to write in Python is going to be named toy node. And then we're going to call that colcon tool, so to make sure ROS knows about it. So let's recap what we did. I have a screen cap on there. Hopefully you can read a little bit of it. But what we just did, we created a ROS Python package named TB4Toy. Inside of that package, there is a node, a program called toy node. ROS did a bunch of setup stuff for us automatically, and then it found our node, and in theory, we could run this thing. There's nothing in it, but we could run it. So let's talk about some advanced, move on to the more advanced stuff. So 80% of ROS is just understanding this concept of nodes, i.e. programs, and topics. That's data transfer. So a node can subscribe to a topic to read data. A node can publish to a topic to write or send data. And all of these topics have a message type. It's a little C++y like that. Everything's got a message type, and those messages and the topics all have a path. So you can almost think of it as like there's message types, and the path for the topics is kind of like a subdirectory where you put messages of a certain kind. So ROS has a ton of CLI tools to introspect topics and a bunch of APIs to deal with them, and you can take a look at the documentation below. So the first thing I'm going to teach you is just a little bit of ROS CLI magic. I'm going to ask ROS to show me all the topics that run in our robot. So if you run a command called ROS2 topic list, you'll get stuff like the topic battery state, and the topic HMI, human machine interface, and the topic OAK-D, which is the stereo camera on the robot. There's another one called scan, and there's another one called ODOM in there. So let's take a look at one of these topics. In particular, I want to take a look at the ODOM topic. So ODOM is a word short for odometry. And if you start the simulation, you click the little play button in your simulator, in Gazebo, and then run ROS2 topic echo ODOM, it will start spitting out as fast as it possibly can all of the odometry information about this robot. And odometry really is just basically the robot's estimate, where the robot thinks it is in the world. And if you look at this message as it's spitting out, you'll see a variable called pose. Inside pose, it'll be position. Inside of position, there'll be XYZ. And that is where the robot thinks it is in XYZ coordinates. So we just did this all with the CLI. You're like, okay, let's get to the Python. So I'm going to show you the ROS Python API for doing publish and subscribe it. And we're going to build something really quick to read ROS topics and read the ODOM topic and print it out. We'll use the node we already created, and we'll do it in like 30 lines of code, and like almost all of that's boilerplate. So first thing we do is we import our odometry messages. So ROS has done a lot of work on the back end to make sure this is in our path and we know where it is. Next thing we do is, so our toy node is just a ROS node. It inherits from ROS node. So we say, oh, well, there's a message called create subscription, and we tell it, let's create a subscription of type odometry on the /odom ROS topic. And whenever we get a new message on that topic, we're going to hit this callback. And the last real bit of real work we do is that we have, when the callback actually gets called, we get a message in the function, and that message has the type odometry, and we can kind of index into it and get our XY position. And so we take that XY position, and we just log it to the screen. Super simple. The bottom of this function, the main, is just some boilerplate that spins up the node, runs the node, shuts down the node when we hit Control-C. So if you do colcon build again, and then you do the command ROS2 run my package name, which is tb4 toy, and then run the node. So don't run it normally like you would with Python. Don't say Python2 toy node. Run it like this. It will hook it up into the running robot, and it will start spitting out the position. And you may not be able to see it up there, but it's just a long line of X, Y, X, Y, X, Y. So that's cool, but like people want to see robots move. So we're going to start sending the robot velocity commands to make it move around. Like before, I'm going to show you CLI commands to motivate your understanding, and then we're going to just do it with the API. So what are we going to do? First, we're going to make the robot move using the keyboard, using another ROS program. Then we're going to do it the hard way with the CLI, and then I'm going to show you how to do it in Python. One thing to know before you start, if you're doing this in person, you're watching this video later, you have to start the simulation by pushing the play button, and you have to undock the robot. Just like a real robot, it's sitting on its dock, you have to press a couple buttons to undock it. So to do the keyboard teleop, what you do is you just say ROS2 run keyboard teleop twist, that's the package name, and then you're going to run teleop twist, the node name. And if you do that, you get this little screen, this little terminal, and you can do what are the game commands? AWSD on one hand and IJUK, and you can drive the robot around. And so this is really helpful to be able to set up scenarios and also to just debug what's going on. I use this a little bit later on. So underneath the hood, this teleop twist keyboard function is just publishing message to a particular ROS topic. It's sending all of its messages to the command velocity cmd_vel topic. And the message type it's sending is a twist message. So all you do to make the robot move is you keep saying, hey, in the X direction, move this fast, and then you send that message in a topic, and the robot does it. And you have to keep sending it messages. You have to give it constant updates. So what we're going to do next is we're actually going to do that with the command line so you can kind of get a sense of how that works and how you would use that to debug, and then we'll do it for real in Python. We're going to need 3 commands: topic echo, interface show, and topic pub. So with the simulation running and the robot's sitting there doing something, let's take a look at this command velocity ROS topic. So what I can do is I can say ROS2 topic info command velocity, and ROS will spit out the message package and the message name. So I see that the type of that topic is a geometry message, or is in the geometry message package, and it's a twist type. Okay, so that doesn't tell me a lot, but it tells me at least what kind of messages I'm dealing with. So then if I use the command ROS2 interface show, and then I put that last output parameter in as the input, so I say ROS2 interface show geometry messages twist, I get what's on the right-hand side of the screen here. And basically, you can actually see that there's some documentation that gets spit out, and it says this expresses velocity in free space broken into its linear and angular components. It's robot jargon. Really what it is 2 vectors, x, y, z each, two 3-point floating vectors of the x velocity, or the linear velocity of the robot, and the rotational velocity of the robot. So this robot can twist around like the z-axis, so you can twist it. So you just learned how to do the robot twist. You now know everything you need to know to make this robot move and turn around. So let's do it with the CLI. So what we do is we basically run a new ROS command called ROS2 topic pub, and we say we're going to use this command velocity topic. We're going to use a message type of twist. Then we write the message as basically in YAML. So you can see the linear component there, and I just say in all directions move to, and in the angular component we rotate. And then there's one little thing at the tail end. I say R-5. That means do this 5 times a second. So you do that, you can actually get the robot to move using a command line. It's not very fast. Okay, so now we know 3 important things, and we can actually do something interesting. We know odometry. So we know that if we subscribe to the odometry messages, if we subscribe to the odom topic and get odometry messages, we know where the robot is. If we publish twist messages on the command velocity topic, we can move the robot. And we also know how to put together a simple ROS Python program, a node. So we put that all together, we can actually build a complex behavior. So we're going to do a barrel roll. I used to have this drone, like maybe, when all the drones got really cheap and you could buy one at like Target for like $10. Had this drone where you would hit a single button and it would do a loop and it'd make you look really impressive. We're going to do that with the Turtlebot. We're going to make it do a little loop in a little function. So building off the previous work, we're going to do this barrel roll. We're going to tell the robot to move in a circle until we return to the starting position, and we've traveled in long enough to be a reasonable loop, because if you don't travel far enough, you're always initially close to the position, right? To do this, we'll need three things. We'll need a bunch of state, so the start position of a robot, the last position of the robot, the distance traveled. We'll need a function that synchronously handles our service requests. So we're going to say, do a loop. There's a function that's going to receive that request and spin everything out. We're going to need a periodic function, think a thread, that handles the velocity commands. And then we're going to need a helper function to do some light math. And I also have to introduce at this point a new ROS concept. It's ROS services and also actions. ROS basically has two primitives for encapsulating complex behaviors. There's services, which are kind of like synchronous quick function calls, what we're going to write. Then there's actions, which are long-running service calls. So if we wanted the robot to vacuum our room and we wanted updates about how much it's done and we want to be able to cancel it, we'd use an action. They're all defined in RCLPy, so they're all in our node. And the one thing you need to remember is that, or need to know, is that these services are defined basically like a ROS message. There's a message in and a message out. One other cheat we're going to use is we're going to use a ROS timer to kick off our thread for us. So before we even begin, we got to talk about requirements.txt files. And in ROS, they're called package.xml files because, unfortunately, we're moving more than just Python. We're moving C++. We're moving all these custom things. So you have to tell ROS, hey, I'm going to use these message types. So you just have to put a little depend flag in your package.xml file. And this is auto-generated for you. And I think you can actually automatically update this in some ways. So let's do it. First thing we're going to do is we're going to import these messages that we just learned about. So we're going to import odometry from nav messages. We're going to import twist from geometry messages. And then we're going to import a service called trigger from the standard services. And if you really want to dig down and understand what this thing is doing, you can use that interface show command again. And so I call that on this trigger message, and it says, I take nothing in, and then I spit out a bool if I'm successful or not successful, and a status message. So the next thing we're going to do is in our init function, we're going to create all those state variables. They're going to be in the function itself, or in the class itself. Oh, most importantly, we're going to create a loop variable. It's just a Boolean that gates all the doing the loop or not doing the loop. And then we're also going to keep track of distance and how close we are to the goal. The real meaty things are that we're going to first create our publisher for command velocity. So we say, ROS, create a publisher on the command velocity topic that takes trigger or twist messages, and then create our service. And our service is going to be called doLoopy, and it's going to take a message or a service request type of trigger, and we're going to pin it to a callback called doLoopy callback. And the last little bit of initiation is that we're going to create this timer function, this ROS timer. And so basically, we're going to tell ROS, hey, every 10 times a second, call this function loop callback. And this will be our main sort of loop where we're sending out velocity commands. So let's get to our service call. So this is the thing that the robot's going to call when you want it to do a loop. And you can see that there's a request and a response in there. Those request and response come directly from this interface definition here. So the request is going to be empty because there's nothing above that line, and then the return value is going to be success in a message because it's what's below the line. Basically, all we do in this function is we reset a couple of our state variables. We set the distance we've traveled to 0. We flip our loop guard variable, and we send a response. So this function really doesn't do that much. Our looping callback That is the thing, say the thing that's running 10 times a second, 10 hertz, is going to be where the action is. Inside of this function, the first thing we do is we check that loop variable. If we're doing a loop, we should do stuff. If we're not doing a loop, we don't do stuff. If we are doing stuff, there's this helper function that I wrote that gets how far we've traveled and how close we are to the goal. And we basically check that to see if we need to unset our loop variable. So we want to make sure the robot's gone a certain distance, in this case 1/2 meter, and that it's within 5 centimeters of where it started. And if none of those conditions are met, this is actually where we publish the message to move the robot. So we create a message that says, move the robot 0.2 in the x direction linearly, and then rotate it -3 about the z-axis. Last function. This is as complex as it's going to get. This is the fancy math. The fancy math is basically Pythagoras' theorem, a squared plus b squared equals c squared. Calculate how each step, each time we call this function, we're going to calculate how far we move from the last point to the current point, and add that up, and that's our distance traveled, and also from our current position to where we started, and see how close we are. So to run this is first we call that colcon program again. So ROS takes the updated function and lets the entire ROS system know where it is. It makes sure that we have all of the message types in scope. If you haven't at this point, you launch the simulation, and then we run our ROS2 just like we did before. ROS2 run turtlebot TB4 toy TB4 node. And the thing we're adding in this case is calling the actual service. So when we want to do the loop, we're going to use this ROS CLI to call the loop. So in that syntax is basically ROS2 service call, the name of our service, and then we have to give it the message type, and recall that it was empty, so we just give it empty YAML. If you do that, your robot's going to go run in a loop when you run that function. I sped this up a little bit, but you've just created your first sort of robot function, and everything is just building up from these little primitives. But we can do a little bit better. We really haven't read any sensors yet. So the Turtlebot 4 and most like Roombas and iRobots, they have on the front of them what I call a bonk sensor, right? When they hit the wall, they go bonk and they turn around and they stop. So I was messing around with this and I realized, oh, we can use the bonk sensor. It's the simplest possible sensor that we can deal with. So the case we're trying to solve for is we put the robot next to a wall, you say do a loop, and it runs into the wall. What's going to happen? It's going to hit the wall and it's going to try to keep going. It's going to like bonk, 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 and it's not going to respond to running into the wall. So we want to fix that problem. So what we're going to do is we're going to find the message that, find the ROS topic that defines bonk and put it into our function. So the way I did this is I went and listed all of the topics running on the robot, and I said, oh, there's this one called hazard detection. What's in that? So I said ROS2 topic info hazard detection, and it spits out that it's using the hazard detection vector. And so then I basically ran that interface command again, and I looked at it, and I see that interface, the hazard detection vector, is basically a timestamp, a frame, which we don't really care about in this context, and a series of detections. And if you wanted to solve this for yourself, what you would do is you'd go run the robot into a wall a bunch of times virtually using the keyboard, and you can use ROS2 topic echo to see this message. And if you look at that message, you start noticing that, hey, whenever it runs into a wall, this detection bit goes from 0 to 1. So let's add it to our robot. First, we update the package.xml, right? We just update the requirements.txt. We import the message type, because we got to let Python know what our message type is going to be. And then we just create a new Python subscription, right? So, or subscription to our new topic. So we say, hey, there's this hazard detection topic. It has type hazard detection vector. Whenever one of these messages pops up, call this hazard callback for me and drop the message in there. Okay, and then we write the callback itself, right? We get a message in, and the first thing we do is we check that detections part of the message. So if there's a list of detections, because most of the time there's no detections because you're not running into a wall, we don't do anything. But if there is a detected type, we kind of parse that message a little bit, and we go look at the part that switches from 0 to 1 when you hit a wall. If we see that that thing is turned into a 1, we unset our gate variable, and then just for safety's sake, to be good robotics engineers, we immediately stop the robot by publishing a 0 twist message, right? 0 out all the velocities and publish the message. We go through this whole rigmarole again where we start the simulation, we run our toy node, and then we trigger the service, but we do it this time next to a wall. And in this case, the robot hits the wall and stops. So we've done all the robot things. We have now successfully created the simplest possible robot. And all I ask is that you use this information responsibly and do useful and wonderful and responsible things with it. And if you need any more information, ROS is a huge developer community. It's in the tens of thousands at least. We have a Discord. We have Stack Exchange that we're active on. We have a discussion forum. We're pretty easy to find if you need help and you want to take this to the next level. And I'm going to leave you with a QR code to go find all the software. And thank you.